Welcome, ninth grade extended students. Today we are going to talk more about parallel lines. The first thing that we need to talk about is the type of angles that can be created when I have a line intersect two others. So you can see in this picture, I have this line L and this line K, and I have a line intersecting both of those. When that is the case, we refer to that as a transversal. And when that occurs, different types of angle pairs are formed. One type is called corresponding. Corresponding angles lie on the same side of the transversal. And the same side of the lines. So let me give you some examples here. So same side of the transversal. Here's my transversal. On the left side are all these angles, A, B, P, and Q. Same side of the lines. I have this line here, this line here. If I go above that line, these two angles, A and P, are corresponding. Also, B and Q are corresponding. They are both on the left and both below the two lines. I can also look at the angles that are on the right side of the transversal. D and S would be corresponding. And also C and R. The other type of angles in our book talks about them just in one foul swoop. They call them alternate angles, but if you look at any other book, they refer to them as either alternate interior or alternate exterior angles. So let me talk about alternate exterior first. Alternate exterior angles are angles that are on the outside of the two lines. And on opposite sides of the transversal. So if we look at our diagram over here, opposite sides of the transversal, left and right, exterior. A is on the left, outside. R is on the right, outside. So A and R would be alternate exterior, and D and Q. Next, let's talk about alternate interior angles. Those are angles on opposite sides of the transversal, but on the inside of the two lines. So here's my two lines. This is the inside. Different sides of the transversal. B and S would be alternate interior. And then finally, C and P. Remember, they are on the inside of the two lines. And on opposite sides of the transversal. There is one more overall type of angle pair that's formed when I have a transversal intersecting two lines, and they're called same side angles. Okay, and again, there are two major categories: same side interior angles, they would be on the inside but on the same side of the transversal. So they're on the inside of the two lines. And on the same side of the transversal. So examples of those: B and P, they're on the inside and they are on the same side, the left side of the transversal. B and P. The other pair is on the right side of the transversal on the inside, C and S. You can see them here, C and S. They're both on the right, both on the inside. There are same side exterior angles. So interior, exterior. They are on the outside of the two lines. And the same side of the transversal. So that would be A and Q, and D and R. So A and Q, D and R. And the other thing I want you to notice is I can have all these different types of angle pairs, and these two lines that are being intersected, they're not parallel in this case, but I still know each individual type. Now, when the lines are parallel and I have a transversal intersecting, it creates some very, very nice relationships. I'd like you to take a minute and name each type of angle pair in this diagram. You'll notice that I still have vertical angles here and still have linear pairs. Also notice there is a typo. I have listed alternate exterior angles twice. Clearly you should only list them once. Press pause on your video, and when you're ready for the answers, press play again. Here are my answers. Press pause on your video so you have time to check your work. If you find an error, check with your neighbor and see if you can't figure out what went wrong. When you're ready to go again, press play. Now, when lines are parallel, it creates some very, very nice relationships. So, if lines are parallel, and that's if and only if, it goes both directions. Lines are parallel if and only if corresponding angles are congruent. And you can look, and I have a nice representative diagram drawn here. Remember, these are your parallel marks. 1 and 5 are corresponding, and you can pretty much see that they're going to be congruent. They're going to be the same measure. Congruent means have the same measure. So 1 and 5 are congruent, 3 and 7 are congruent. All sets of corresponding angles are congruent. Alternate interior angles are congruent. Alternate exterior angles are congruent. And once again, I listed this more than once. I don't know why. And same side interior angles are supplementary. This guy and this guy, supplementary. This guy is supplementary. Same side exterior angles are also supplementary. 1 and 7, 2 and 8. You'll notice I have nothing listed here about linear pairs and vertical angles because their relationships do not depend upon whether the lines are parallel or not. vertical angles like 1 and 4 are always congruent. Same linear pairs are always supplementary. 1 and 2 are always supplementary. But these pieces are only true when lines are parallel. And then likewise, if I have two lines and I don't know that they are parallel, if I can find a set of corresponding angles that are congruent, then I know that they're parallel. That's the if and only if part. It goes both directions. EMF names all these theorems, says A2, but we're going to write them out. So it says if lines L and K in the plane pi are distinct and are crossed by a transversal, then the angles of corresponding pairs of angles have the equal degree measure if and only if L is parallel to K. Angles of alternate pairs of angles have equal degree measure if and only if L is parallel to K. And they leave out the part about the supplementary. But we're going to write all of our theorems out completely in words. Again, what's always true? Vertical angles are always congruent. It doesn't matter whether or not the lines are parallel. Linear pairs are always supplementary. It does not depend on lines being parallel. Okay, in this diagram, I am given that C is parallel to D, and I didn't label them, so let's do that. And I would like to find the measure of angle 1. Okay, let's take a look at what we have here. These are alternate interior angles, so that means that they have to be congruent. So let's set them equal to each other. I'm going to solve for x. I'll subtract 2x from both sides and subtract 5 from both sides. But this is not my answer. I got to be really careful. I want to find the measure of angle 1, which is here. Now notice angle 1 and this angle are vertical angles, so they have to be congruent. So if I substitute back in, I find it's equal to 15 plus 5, or 20 degrees. I'd like you to try to find the measure of angle A. Notice there are no parallel lines in this picture. You're going to have to rely on vertical angles and linear pairs. Press pause on your video. When you're ready for the answer, press play again. Okay, here's my answer. Notice the relationship I can see is that this angle and this angle form a linear pair, and they're supplementary. So that means their measures have to sum to 180. So I wrote this over here, this equation, and I solved it. But to solve it, I need to solve a quadratic, which means I need to factor it. So once I get here, I set it equal to 0. I need to find two numbers that multiply to negative 192, but add to positive 4. And it did not come to me in a vision, so I made myself an organized list. And I got to where I knew 12 and 16 multiplied to 192, and then I noticed their difference was 4. So those were the two that worked. So I found that x is equal to 12 or x is equal to negative 16. Now in this context, remember, we have to have positive measurements because angles are never negative in measure in geometry. Not till trig do we allow that. So now I need to find angle A. If I put negative 16 into this measurement here, I'd have a negative angle. And again, that's not allowed. So substituting in just the 12, I find this angle here is 100 degrees, and these two angles are vertical angles, so I know that they are congruent. The next type of problem I'd like to look at is called a crook problem. I have a set of parallel lines, and I have the segment in here that's bent. This is the crook. And I'd like to find the measurement of that angle. And it's really easier than it appears. The trick of it is that I have to draw myself a line that is parallel to those two through the crook. And once I do that, I can see that I've created alternate interior angles here that are congruent. And these two angles are same side interior angles and they're supplementary. So I know that this angle here is 40 degrees. And then if these two are supplementary, and this is 100, I know this is 80 degrees. And then I know that the measure of angle 1 has to be 40 plus 80, which would give me 120 degrees. So again, the secret to doing this kind of problem is always drawing a line through the bent corner inside those parallel lines, and sometimes there's more than one. All of those parallel lines theorems can be proven through translations. So if you notice that I have this transversal here and I have this line parallel to this line, I could translate this line to be on top of this one, and we would see angle B is congruent to Q, C is congruent to R, and all the different ways those are related. So I could translate this guy up here. I could see that P and S are congruent. No, P is congruent to A, S is congruent to D, Q is congruent to B, R is congruent to C. So for a formal proof, an EMF style proof, see exercise 219. I have put that in as a model answer. Now I'd like to talk about another type of mapping. Remember, I can assign points in the plane any way that I'd like. So we have a different mapping defined over here. Let's read through it and see what's going on. So we're going to let pi be a plane, and we're going to let L and K be distinct intersecting lines in pi. So here's L, here's K. By the parallel postulate, we know that for each x in pi, there's a unique line M in pi that both passes through x and is parallel to K. So for example here, if I chose to name this point X, there would be exactly one line that passed through X and would be parallel to K. Let the mapping P of KL from pi onto L, so my domain is the plane, my range is L, it's onto L, be defined as follows. For each X in the plane, the image of X is the point of intersection of L and the unique line M in pi that both passes through X and is parallel to K. So let's take a look. So if I have this point X, it's going to get mapped to my line L this way. So I would draw my line that's parallel to K through X and map it onto the line. This is very similar to the perpendicular projection, except these lines are not perpendicular to L. They are parallel to K. So P sub K comma L is called the projection of pi parallel to K onto L. In the diagram on the right, we show some points and their images in a typical situation, and now there's some exercises related to this mapping. So again, I can find any image by drawing the line through that point, parallel to K. It gets mapped to the intersection of my parallel line and L. Any point that is on this line gets mapped right back to itself. So take a minute, try exercise 221, press pause on your video, and when you're ready for the answer, press play again. Okay, the first question says, is this mapping one-to-one? And the answer to that question is no, because if you think about where all of my points were getting mapped, they're all getting mapped onto the line. I have a lot of different points being mapped there. Any point that is on this line that was parallel to K gets mapped to this point. So it's not one-to-one. It has more than one arrow in. Does it preserve distance? Absolutely not. Look at these points here. This guy and this guy. There's a distance between them. When I map them, there is no distance between them, so it does not preserve distance. Then I'm asked to compare P of K comma L with the mapping F of L in exercise 163. What would the relationship between K and L have to be in order for them to be the same function? So that is that perpendicular projection that I was referring to earlier. So in order for them to be the same function, K would have to be perpendicular to L. Okay, I have posted an assignment on Schoology, so take a look at that, work on that assignment, and we will move on from there tomorrow. The next topic is going to be parallel lines proofs. Have a great day.